In this video, we're going to be graphing rational functions. I'm going to show you two different forms and some shortcuts you can use if you happen to see functions in either of those two forms. First form will look something like this. So in general, we have 1x, and everything else, all these other letters will be a number instead. So in general, we want things that make the denominator here equal to 0. We're going to talk about what happens with that. And then we'll talk about, so if x equals h, and also what k does over here. So jot those down really quick, and we'll talk about what each of them mean, and we'll use a real example here. Alright, so this is in this form. We want to find a value for x that makes our denominator equal to 0. Remember that a 0 denominator is an undefined expression or an undefined value, undefined graph. It's just undefined. And so we are going to see graphs that stop at this value that makes our denominator equal to 0. So what value of x would make our denominator 0? Well, the opposite of h, so instead of positive 3, it would be negative 3. We're going to draw this as a graph, and this is actually called an asymptote. An asymptote is a line in which your graph will approach. It will come near that line, but it will never touch it. And for equations that have an x equals, those are vertical lines, so this will be a vertical asymptote. Y equations, or places in our graph that our graph won't touch, but will get as close to as possible without touching horizontally, are the values out here, the k values. So y equals k, in this case it would be y equals negative 1. That would be our horizontal asymptote. So our graph will approach that horizontal line but never touch it. So let's look at this in graph form. It'll hopefully make a lot more sense. We'll rewrite our function. So we know that our vertical asymptote is this vertical line at x equals negative 3. So while the asymptote is not generally graphed, it's always implied. It's always nice to either use a crayon or a marker to mark it on your graph, just so that you're aware that you don't want to touch that line. And the more colorful you make it, the more obvious it is, and the better it helps you when you're graphing. So our graph will not touch this line. What was our other one? Our y equals negative 1. So at y equals negative 1, that will be another asymptote. We'll see what happens when we actually graph this function. Let's come up with an xy table. Remember, you can use an xy table anytime you don't know tricks to graphing. If you just use an xy table, substitute a value for x and get an output, you should always be able to graph a function regardless of what it is. So my tip for you is to use values that make this really easy. So try not to use fractions when you're graphing, or anything that's just really hard to put on a graph. So in general, if you use x values that are to the left or right of your asymptote, those are good values to use. Or y values, if you're doing inverses, would be above and below your asymptote here. So let's use an x value to the right of this vertical asymptote. So if I use -2, what happens? Well, -2 plus 3 is +1. -2 divided by +1 is -2. And -2 minus 1 is -3. So we used -2 and we got -3 out of it. So -2, -3. Let's try -1. If we use -1, we get a +2 on the bottom. -2 divided by +2 is a -1. -1 minus 1 is -2. So -1, -2. At this point, I'm going to jump ahead and just tell you what this graph looks like. In general, rational functions are going to have this shape called a hyperbola. It's kind of like a parabola, except it doesn't have 2 legs, it only has 1. And all rational functions are going to have hyperbolas because they're going to have these asymptotes. And in general, you can always cheat. As long as you come up with 1 or 2 points of rational functions, then you can basically just graph an idea of that parabola. Unless you're asked to specifically provide exact points, you don't necessarily need to, because a lot of times you're just trying to get approximations of graphs. So I only use 2 points, and I know this is a hyperbola, so I know that as it goes this way, it's going to approach this vertical asymptote. It's going to get closer and closer and closer, but never touch. And on the other side, it's going to approach this horizontal asymptote. It's going to get closer and closer and closer and closer, but never touch there. So the hyperbolas are always going to do a similar shape in a similar direction, and they're always going to be nudging towards your asymptotes. And then another nice cheat is that the asymptote is, or the other hyperbola is always on the other side, and it's just an inverse of this. So because this is going this way, the inverse of this one would be something like this. So this hyperbola is getting closer and closer to this asymptote but never touching, and as it goes in this direction, it's getting closer and closer to this asymptote but never touching. And so it's a really nice, quick way of graphing rational functions. As long as you know where your asymptotes are and you pick a couple points that are nice and easy to plot, then you can approximate your graph pretty quickly here. So let's try another one. We're going to have a different form this time. If you see rational functions that have 2 x's, 2 inputs, then you're going to be able to approximate the asymptotes in this way. Your vertical asymptote, or the x equals equation, is still going to be whatever your denominator equals, and makes your denominator equal 0. But the horizontal asymptote, or y equals equation, is going to be slightly different. This is going to be whatever the coefficients of your x values are. So a over c is going to be the y equals equation, or your horizontal asymptote. So let's do a real example using real numbers. So we're asking ourselves, what x value makes our denominator 0? Well, you could solve it if you set it equal to 0, if that helps. Sometimes you can get it pretty quickly. Sometimes you're going to have to set an equation equal to 0 and solve it. So if we add 4 to both sides, we have 2x equals 4. And then if we divide by 2, we get x equals 2. So if x equals 2, our denominator becomes 0, and our function is undefined. So that means that this is our vertical asymptote. Let's look at the y, or horizontal asymptote. The coefficients, so there's an invisible 1 there. So really we have 1 over 2. So at 1/2 on the y-axis, we're going to have a horizontal asymptote, where our graph will not touch. So let's see what that graph looks like. X plus 1 over 2x minus 4. Our x was at 2. So right here is our vertical asymptote. And then at y equals 1/2 was our horizontal, so about right here. So our graphs are not going to touch either of those lines. Let's figure out where our hyperbolas are. Let's put a couple points on our graph. So again, if we use values to the left or right, if we use 1 or 3, it should be fairly easy. Let's see what happens here. If I use 1, then I get 2 times 1, that's 2. 2 minus 4 is negative 2. And on top we have 1 plus 1, that's 2. So 2 divided by negative 2 is negative 1. So at 1, negative 1, that's a point on our hyperbola. So already I can tell that our hyperbola is going to do something like this. It's going to come closer to that line, and as it goes down it's coming closer and closer to that line. And then I also have the inverse over here. And again, it's not exact, it's just approximately something like that. So again, I only use 1 point because I'm more familiar with hyperbolas, but we could use another one. Let's try 3 and see what happens. Make sure we did it right. If I input 3, that gives me 2 times 3 is 6. 6 minus 4 is 2. 2. And then up top I have 3 plus 1, that's 4. And 4 divided by 2 is 2. So at 3, 2 is the point on my other graph. So you got a pretty good approximation there. So again, rational functions will always have hyperbolas in the graph. As long as you can figure out 1 or 2 points, you have an idea of where your hyperbola is. And the nature of the hyperbola is always the same. It's always going to approach your vertical and horizontal asymptotes but never touch. And all of those things combined gives a nice, easy, quick way of approximating the graphs of our rational functions. Also in general, domain and range is something we're going to be talking about in the next few videos. Domains are possible inputs or possible x values. For rational functions, the domain is always going to be all real values or all real numbers, anything on our number line, except where these asymptotes are. So where x equals 2 is never going to be a part of our graph, so we say all real numbers except x cannot equal that asymptote. X cannot equal 2. And our range is very similar. It's, again, always all real numbers for rational functions except wherever this horizontal asymptote is. So y is all real values except y cannot equal, in this case, 1/2. So in the next few videos we'll be talking a lot more about domains and ranges and listing them as we graph. So just in general, domains are inputs or x values, and they're always going to be all real numbers that are possible for rational functions. Ranges are always talking about y values, values on our y-axis here. And again, they're also going to be all real numbers except wherever that horizontal asymptote is. Alright, so good luck graphing rational functions in those two different forms.